Hello, I greet you. My name is Aisha Avataris and I am the Chief Communication Officer at oetti-ds, a consulting company for data science and AI. Everyone is talking about agentic AI as the new hype topic in the field of artificial intelligence, and today we want to specifically show you how to build an AI agent. Agents are not a new topic, as software agents have existed for a long time. They take on tasks and process them independently. These are workflows that automate a programmed sequence of actions. All steps and branches are hardwired and must be defined in advance. Some already speak of AI agents, when individual work steps are supported by an AI component. For example, a website contains a chat function, where the chat is supported by an LLM. However, the actual workflow and thus the sequence of actions are still hardwired, and deviations must have been programmed in advance. Therefore, one cannot yet speak of an AI agent, but merely of an AI-supported agent. A small but crucial difference. It only becomes a true AI agent when an intelligent agent decides on the branches in the workflow, selects the tools used, and monitors all the steps in the workflow. So, the entire process with all possibilities is not programmed in advance, but it is left to the intelligence of the agent to design the process in each individual case. Multiple AI agents can also be combined or structured hierarchically, where a superior agent controls one or more subordinate AI agents. And it is precisely the creation of such a hierarchical agent that I would like to demonstrate today. I am using Langflow as the software platform. Langflow is an open-source tool that serves as a visual interface for creating agentic AI applications and workflows. It is Python-based and allows the integration of AI components, LangChain objects, and APIs of all kinds. In addition to the open-source access, Langflow is also distributed by the vector database provider DataStax. DataStax was acquired by IBM, but Langflow is expected to remain freely available as open source in the future. Langflow can be downloaded locally on the desktop as a Python library, or used for free in a hosted version on the DataStax website. Downloading in a virtual environment with UV is recommended, as pip and pips downloads have caused more complications for us. UV is very fast and straightforward in downloading packages. Langflow offers a graphical interface where different components can be combined into an AI application via drag and drop. There are components for chat, DAVIO, or text input, for output, and for prompts. Furthermore, you can connect different data sources. Components for data and text, as well as process steps, are available. A core part of the component collection is the connection to virtually all major LLM models. An API key is required for their use. I'll show you how and where to get it later in the video. By the way, for each component, you can always view the underlying Python code and adjust it if necessary. You can think of the components as a visual representation of pre-made code snippets that you can combine codelessly in the graphical interface. Access to the Python code is consistently available. A larger number of connectors to vector databases are available. Vector databases are important in conjunction with large language models because they enable similarity searches in multidimensional vector spaces, which relational databases cannot do. It sounds complicated, but this should suffice as a note for now. I will explain the principle of vector databases, and the necessary embeddings, in more detail in another video. Another core element of the available components is the agent component. It forms the intelligent control center of a workflow. The intelligence comes from an LLM model, and the instructions are used to guide the agent on how and which tools to use and how to handle the results. Memory components allow chat histories to have a memory. Furthermore, a toolbox of tools is available, such as search APIs, MPC servers, connectors to Wikipedia, calculators, and much more. There are a number of logic components that enable loops, branches, etc., In addition to some helpers, there are also the so-called bundles from various manufacturers, which are pre-assembled collections of components for a specific purpose. If that's not enough, you can create your own component with Python. For this, there are the custom components. The Langflow documentation describes how to define your own class with Python code, which then provides the desired function. Let's now take a look at creating a very simple workflow for the first time. For this, we take a chat import and a chat output component, place an OpenAI model in between and connect them. We can choose the version of the ChatGPT model and need an OpenAI API key. This can be generated as a registered user on the OpenAI platform. To make the key work, you need to deposit a few dollars into the OpenAI account. The prices for using the key are given per 1 million tokens and depend heavily on the chosen model. As the fourth component in our workflow, we need a prompt component, where we provide instructions for prompt creation. We insert the newly created key into the appropriate field and can test if the component works by pressing the Start button. Now we look at the result on the playground. We ask a question and indeed receive the corresponding answer. Our workflow does what it is supposed to do. To avoid entering API keys every time, you can save them as a global variable. To do this, go to the settings and save the key under the appropriate category. This way, it is automatically displayed as a suggestion in the components and can be directly adopted. A central component of Langflow is agents. Agents use tools and, following appropriate instructions, independently decide on the most sensible use of these tools. For an agent to use a component as a tool, the tool mode must be activated in the component. Then the tool set appears at the output of the component and can be connected to the tool input of the agent. Thus, the component's toolbox is available to the agent. Multiple components can be connected to the agent. However, one should not overdo it with the number of connected tools and especially avoid overlaps in the functions of the components, as this can overwhelm the agent or make the instructions too complicated. In this example, we have connected a Google search engine, Yahoo Finance data, and a Wikipedia connector to the agent. To distribute and structure tasks, hierarchies of agents can be created. For this purpose, an existing agent is defined as a tool and can then serve as a tool for a superior agent. In this example, we have a second agent, which we also define as a tool and assign to the superior agent. This creates a two-tier hierarchy, consisting of a superior agent that controls two subordinate agents and distributes the tasks. Next, I would like to show you how to extend a large language model with a vector storage. RAGE, Retrieval Augmented Generation, refers to a software system that supplements the information from a large language model with additional own information sources, such as documents, databases, or websites. A query to the LLM then accesses not only the model's training data, but also the additional information. This increases the accuracy and robustness of the generated content by providing the models with current and specific information. Typical use cases include chatbots accessing internal FAQ documents or other factual information from reliable sources. This additional data cannot be stored in a normal relational database, but must be available in a vector database so that the LLM can process the information. The explanation of why this is the case would deviate too much from the topic of this video, and I will show you this in more detail in another video. DataStax offers a scalable vector database with AstroDB. The first part demonstrates how, for example, data from a text file is read into this database. For this purpose, the texts from the file are first split into individual components and then added to the vector database using an embedding component. Embeddings are numerical representations, i.e., vectors, that map the content or semantic value of data in a multidimensional space. The focus here is that similar content receives similar vectors. So they are close to each other in the vector space. But as I said, I will explain this in more detail in another video. Retrieving the information stored in the vector database can be imagined as follows. With the input from the chat request, the vector database is first checked to see if information is available. The result of this query is parsed and added as context to a prompt, which is then sent to the LLM. So, the prompt is the original request supplemented with the relevant information from the vector database. The result provided by the LLM thus incorporates the information from the vast training data of the LLM with the specific knowledge of the vector database and delivers a combined response. The next topic I would like to address is the integration of additional functionality via MCP servers. MCP servers are interfaces that enable the provision of data and functions from external systems for AI applications. Integrated into Langflow, they significantly expand functionality by enabling standardized communication between AI models and external tools or data sources. There are currently almost 50,000 MCP servers that are registered. It's still quite a bit of a Wild West situation, and it's not always easy to find actually functioning and trustworthy servers, but the possibilities are almost limitless. The Model Context Protocol server is an open standard protocol developed by Anthropic to simplify interoperability between large language models and external systems. By integrating MCP servers into Langflow through the MCP server component, access to external data sources can be enabled, functionality can be significantly expanded, and they can be integrated into complex agent workflows. There are different directories that provide an overview of existing MCP servers and list information on installation. A useful server directory can be found on GitHub, where installation instructions are also provided. A similar directory, is offered by mcp.so and smithery.ai. As an example, we want to show how to connect a Google Maps server. In the GitHub entry, we find the information on how to install it using an npx command. We extract the corresponding npx command from the JSON file and insert it into the MCP command line in the MCP Langflow component. After establishing the connection, the tools of the MCP server are available and can be used in the Langflow workflow like an internal tool. In addition to the over 70 internal Langflow components, one has access to literally tens of thousands of additional tools via the MCP server. If that's not enough, you can insert any Python code through a custom component and expand the functionalities as desired. You just need to adhere to the guidelines described in the documentation. In the example, we programmed an if-else component and can then integrate this functionality into the workflow. Langflow can not only integrate MCP servers, acting as a client for MCP servers, but it can also become an MCP server itself, or more precisely, make its workflows available as an MCP server. With the MCP SSE extension, the URL of the Langflow installation can be specified in the SSE connection of the MCP client. We have installed Langflow locally, and therefore, the link to the local host needs to be entered. Here, we connect the MCP components with the MCP SSE URL of the local host, and then all defined flows on this instance are offered under the tools, allowing us to use them like any other tool from Langflow components. So, now I have provided an overview of the most important functions of Langflow and would like to summarize them here. Once more, Langflow offers over 70 components for the integration of LLMs, databases, web search, retrievers, etc. All common LLMs can be easily integrated via APIs. Langflow can be installed locally as a Python library or used online in a hosted version by DataStax. A hierarchical agent structure is possible. It is completely based on Python. The code of internal components is transparently visible, and custom code can be seamlessly integrated. MCP servers can be integrated via the MCP client function. Defined workflows can also be made available as MCP servers. If this sounds like a promotional event for Langflow, I can assure you that we operate independently from oetti-ds, and we're neither commissioned nor paid by Langflow for this video. As impressive as Langflow's capabilities may seem, it cannot be denied that many problems arise in detail and in practice. The download doesn't work right away. Necessary packages are missing, which have to be laboriously loaded afterwards. There are difficulties in the integration of MCP servers, and some components still seem immature or faulty. It's simply a relatively young product with one or two teething problems. However, the basic idea of the product is brilliant, and the potential for real success definitely seems to be there, and we don't really see any comparable offerings on the market. We are definitely impressed by Langflow. In the next step, I would like to outline a complete use case from the HR sector and create a multidimensional AI agent workflow. It's about analyzing a candidate's resume and creating a summary. The workflow is divided into 3 independent steps, each controlled by an agent. The overall coordination is carried out by a superior agent. First, the application document is analyzed. Then, in the second step, information about the applicant is gathered from different sources. And in the third step, a self-developed model is applied to predict the success and expected tenure of the applicant in case of employment. The unstructured API component is used for analyzing the CFE document. Unstructured I/O is a software that creates structured data from unstructured documents and outputs it in the desired format. You can test the software for free and create an API key, which you enter into the Langflow component. The agent uses this together with the unstructured output component to output relevant information from the resume in a structured form. The second sub-agent strand is the information collector, which gathers data about the applicant from various sources. Firstly, a web search is conducted. Secondly, an internal database is checked to see if information about the applicant already exists. And thirdly, data is collected from LinkedIn via an MCP server. In addition to the API key, the agent requires a detailed instruction on how and from where to collect the data and in what form. This instruction then serves as a basis for the agent's decisions on which tool to use and how to compile the researched data. A Google Search API is used for the web search. An Astra vector database is available as the internal database. For this, the intelligence of an embedding component is needed again to find the appropriate entries. As a third component, information from LinkedIn is to be collected. For this purpose, an MCP server for LinkedIn is used, which we found through Smithery. The npx commands necessary for the connection are taken from the corresponding JSON description on Smithery. As a reminder, it should be mentioned again that all 3 components must be set to tool mode so that they can be used by the agent as a tool. The output of the agent is converted back into structured data via a structured output component. The third sub-agent strand consists of a self-created machine learning model, which is intended to predict, based on the previously determined applicant data, how long an applicant would stay with the company if hired, and how successful they would be. The model was trained using data about the company's existing employees. Technically, it is an XGB model that was exported as a pickle file and can now be imported and used in this custom component. This is done via Python code. If you want to learn more about how machine learning models are created and applied, I refer you to the corresponding video on this oetti-ds channel. So, we have now created 3 individual flows and want to compile them into a complete flow. For this, we use the capability of Langflow, which I have already explained before. Flows can serve as MCP servers. The idea is to integrate the individual subflows into the overarching complete flow via an MCP server component. You connect the MCP server component with the local host and then have all the previously created flows of this instance available as a tool. So we insert 3 corresponding MCP components into the complete flow and connect them with the main agent. This agent coordinates and consolidates the results of the 3 sub-components and, using an SK structuring component, outputs a table with the data, key figures, and scoring values from the forecasting model as the result. A note on the technical aspects of the use case presented here. The result from this pre-qualification process should, of course, never be used as an automatic decision model, but merely serves as automatically generated additional information that can support the decision of the key personnel from HR and the specialist department. Furthermore, it should be noted that the workflow presented here is merely a sketch intended to illustrate the basic principles of the agents. The actual workflow is more complicated and contains far more components.